When we analyze the Adelic Langlands program, we find that J-space operates differently than a continuous geometric subspace. Instead, it functions as a discrete mathematical rendering engine that translates raw arithmetic into reportable geometry. This master equation partitions the physical state vector. The left side, the sparse sum, is the active workspace, containing patterns that render as visible physics. On the right, the residual vector R absorbs all invisible, chaotic quantum tracing. By mathematically severing these two components, the system protects the active geometry. The clear, continuous reality we perceive holds together because all the underlying algebraic chaos is systematically filtered out and trapped inside this residual vector. To project raw Satake eigenvalues onto that active workspace without causing basis drift, the Jacobian lens utilizes this transition matrix, TP. Mapping the S3 permutation group shapes the geometry. The complete split matrix expands symmetrically down a 3D cone. The branched fold zeroes one channel, collapsing into a 2D face. The inert chiral state applies cyclic rotation, forcing the vector to clip discrete corner rays. To keep these geometric deformations stable, we apply the Sinkhorn-Knopp algorithm. Looking at this normalized matrix for the branched fold, it balances the local activation energy. This normalization strictly locks probability flow between 0 and 1, ensuring these shifts never trigger a total geometric collapse. This block diagram illustrates the absolute dimensional bottleneck. At prime p equals 2, exactly 1/7 of the model's total operator volume is mathematically locked into uninvertible sheet couplings. Thus, the absolute upper bound of independent token directions you can safely activate is exactly 6/7. Let's test this constraint. If you have a J-space activation layer with exactly 70 dimensions, what is the maximum number of sparse tokens you can safely track at once? Take a second to calculate the limit. 6/7 of 70 gives us exactly 60 safe tokens. If you attempt to force a 61st token into the active dictionary, the uninvertible core overflows. The extra phase twists mix destructively, completely destroying the local flat geometry of the space. This strict parahoric bottleneck dictates the physical structure of our universe. Matter appears as sparse, highly localized points rather than bleeding, across all dimensions because any excess topological complexity is strictly forbidden from entering the active geometric workspace. Where does the uninvertible data go? The Picard-Fuchs differential equation governs the residual vector. Its timeline reveals 3 singular points of phase shifts: the collision core at t equals 0, the sheet transition at t equals 1, and the boundary at infinity. Near the core singularity, local solutions split into a stable branch and a violently divergent branch. The divergent branch, R2, scales to -1/7. This trajectory acts as a topological shock absorber, scaling up to swallow numerical kinks generated by non-injective information leakage. The entire J-space pipeline operates on this precise balancing act. The physical state is partitioned. The active geometry is strictly capped at 6/7 of its potential dimensionality, and all excess metadata is trapped in a decaying residual trajectory. The macroscopic physical laws we observe remain smooth, stable, and perfectly flat, solely because the raw, uninvertible friction of the universe is eternally exiled to this hidden mathematical dimension.